Hello, everyone. I'm Mikołaj from Department of Artificial Intelligence at Wrocław Tech, Wrocław University of Science and Technology, and I would like to present to you my and Janek paper, also presented at ICDM conference 2 weeks ago at the same workshop, Centira. And the paper is entitled Divide, Cache, and Conquer, Dichotomic Prompting for Efficient Multi-Label LLM-Based Classification. So let's dive into. I want to start with a motivation that drove us to this topic. So at our university, we have at Clarin PL an service tool called Imotagger. So it is actually just as the name suggests, a tagger for emotional affective analysis. So if you put to it some text, then it analyze it and classify which emotions, which affective states it exhibit. And what are the main challenges in the affective computing and affective analysis? So as actually Janek said in the previous presentation, the subjectivity. So for one person and for another one, the affective states might not be the same. So for one person, the text might be positive, and for another might be negative, and so on. Also the concept drift. So if when our language evolves, then another labels occur more often. For example, cringe hype. These terms wasn't that hyped a few years ago, and also high overlap of these labels. So one text can be classified as joyful, positive, and so on. Also, in our cases, actually, we sometimes label one text as positive and neutral, or positive and negative at the same time. So this overlap is very high. And developing for this Imotagger a model that is actually dynamic is very crucial, and it's not easy task. So as you can see, we have this dynamic data. So the texts that we want to label for specific affective states, then we want to have a model that is very flexible, not rigid, and also possibly accurate and not very expensive, slow, which is just efficient. So if we have models that are standard, so encoder-only language models like BERT and this kind of stuff, then if we want to have other affective states to classify, to label, then we need to retrain the entire model. And this is not feasible often. So we want something that is more flexible. And then we have modern decoder-only large language models like GPT, Qwen, DeepSeek, and so on. But they are very slow. So we want to compromise these two roles. So we would like to have a decoder-only large language model that is flexible, and also we want to reduce some computation cost of such a model. So the standard case, the standard approach of multi-label classification using decoder-only LLM is something called structured JSON output. So we start with our single prompt, the instruction and the text to classify, and also provided schema with the labels that we want to be classified. And we put it to our decoder-only LLM, and it processes the entire prompt and output with provided schema the labels classified as true or false. And what are the problems with this approach is that it's very complex because if we have a lot of labels, hundreds or even more, then the entire output is very large and also very fragile, because sometimes even the most recent models have problem with processing the valid JSON in the final answer. And also the generation is kind of slow because we see that the model needs to generate all this valid JSON format, and it's just expensive for such a model. And we want to some kind of reduce the computation time and make the problem for this decoder-only LLM just simpler. So we did something that we call dichotomic prompting. So we decompose the entire multi-label classification problem to simple binary queries. So, for example, if we initially had 3 labels, joy, sad, and irony, in our standard JSON schema, then we decompose it for 3 independent queries, and we process it independently with this LLM. No zero JSON schema and so on, just simple binary queries, and the model needs to answer yes or no for each query. And this make the entire problem very simple for this model, very robust, because we just need to ensure that the model produce yes or no, or this dichotomic kind of answers. And also this approach can be parallel visible, so it makes make the entire approach more feasible and efficient. But you can think that if we, in our standard approach, we have just one request to a model, and now we decompose the request. For example, if we have 20 labels to classify, then we need to put 20 requests for a model, and it sounds even slower. But we benefit from that. We have decoder-only large language model, and then we have in such models something that's called KV cache, and if we put a request to the model that share the same prefix every time, so the instruction and the text, and we only change for each request the label that we need, that we want the model to classify, then we compute the entire representation, we process the entire long prefix just once. We benefit from that. We have KV cache, and we only need to process this one token or several tokens from the part that we change from for the classifier. So we compute it only once, and the computational overhead that we have from decomposing the entire problem is very low, actually. And with this approach, we, as we can see, we get rid of this very fragile and complex structured JSON output, and we only decompose the entire problem into very simple yes/no questions. And as you can see, the computational overhead, once again, is very, very low. And we want to somehow evaluate our idea, so we collect from different sources data set that consists of, in total, 10,000 Polish texts with a context of news, social media, reviews, and academic texts, and also 5 topics: politics, sport, science, products, and culture, each 2,000 texts, and 24 labels, affective labels, so the sentiment and other affective dimensions, like joy, anger, sadness, and so on. And I want to briefly present the methodology of the distillation pipeline, because we didn't have annotated text, only the raw text without any labels, and we want to distill the knowledge from some very large model, and then train small decoder-only LLMs. So we have these 10,000 Polish texts. We annotate with DeepSeek v3, and I will discuss it in a moment. And also we have some human check that we ensure the annotation process is correlated with the human annotation. And finally, we fine-tuned some LLMs that are actually SLMs, because they are small language models. So the first step is to, for every text, we have 3 passes to 3 requests, independent requests to DeepSeek v3, and we have 3 sets of pseudo labels as the output. Then we aggregate the output as the majority vote, and we also conduct some human validation check. So on the subsample of 200 texts, we do the human validation check, and the PSA positive specific agreement was above 0.8, and also Cohen kappa was about also 0.8, something like that. So this was very high. and we annotate the entire data set later with this DeepSeek v3 with this majority vote 3 passes approach. Yeah, and we see that later we fine-tune our student models, our small language models, the decoder-only ones, evaluate them, and we will see in a moment what are the actual results. Also, I want to briefly talk about our evaluation protocols. So we will have in distribution settings when we train fine-tune our small language models on all the 24 labels and also test on all the labels. And our different setting is out of distribution, OOD, when we train on 24-1, so 23 labels, and on the left one out label we will test it to see whether the models can generalize to what they didn't see during training. And these are the performance results. And we can see on right, we have the standard JSON structure output. So this is these ones. And on the blue, we will see this dichotomic prompting setup. And also as a baseline, we got this Herbert model, which is a standard model encoder only language model to just ensure that our approach is not worse than the standard approaches that people use nowadays. So we can see that actually the results are very similar to each other, and we have not any performance drop switching to our approach instead of using encoder-only models and the standard JSON structured output approach for decoder-only models. And also for the out-of-distribution setup, the generalization that we want to test, we see that our dichotomic prompting approach, if we don't fine-tune any the model and we just prompt it, but not in the standard way with a JSON schema and so on, but decomposing the entire problem into k independent labels, then actually the results are even better than the JSON standard output. And we also see on these results that if we fine-tune the model, then we are into some kind of trap, I would say, because the model cannot generalize well. So if we train on some subset of the labels and we test on the another label that the model didn't see during the training, then we go for a phenomena that is called catastrophic forgetting. So the model just lose the ability that it had before our fine-tuning. And I want to discuss our main, I would say, result. So what is the efficiency of our approach comparing to the standard JSON structured output? And as you can see, on the x-axis, we have length of a text measured in the tokens, and on the y-axis the total time for the processing. As you can see, that if we have short text around to 4,000 tokens, then our approach is actually 2 to 3 times faster than the standard JSON structured output. And after that, our approach is getting slower, and we hypothesize that it is because we cannot fit in our memory, we cannot cache everything if it is too large. So it is hardware dependent, but if the text is getting larger than it can fit into the device memory, then our approach is getting slower than the standard one. But if the text is rather short, which is rather the domain of the affective computing, then our approach is 2 to 3 times faster, and this is the main the key takeaway from our results. So I want to just summarize what we did and what's the conclusion. So combining our approach, dichotomic prompting, with this KV cache, prefix caching, we can have a flexible decoder-only language model that is flexible because it is decoder only, and we can prompt it for any label that we actually want to, which wouldn't be feasible for the standard encoder only models, but like style because of the architecture. It is efficient for short texts, as we saw. It is 2 to 3 times faster than the standard JSON structured approach, and it is also scalable because we don't need to have any specific ability for language model to just decompose our problem from multi-label classification at once to binary independent classification for each label. And yeah, that's actually it from my side. Thank you for your attention, and I will be happy to take your questions.